Great, so what I want to do now is go back to our discrete and our integral approaches and revisit those problems using Python so that we get comfortable using Python, especially for this tutorial where I would like you to try and give that weak form solution a Python go. Okay, so that is that, but I don't want to give you a sort of a solution that's already worked out for that specific problem. I want to just go to back and recap sort of before we derive the weak form for the weighted integral problem and say, let's see if we go and solve these using Python, what do we learn? And make sure that we interrogate and also reflect a little bit on the answers and whether they make sense. Okay, so what I want us to do is, first off, what I want to just show you is if I toggle on this notebook here, click here on and off, that's essentially what happens here is that it hides the code. Okay, so that you can look at it as a sort of a notebook that you can read through quite easily. And if you click here, it will show you the code, and then you can look at interrogate the code. But what I want to do is I want to look at the code. So I'm not going to untoggle it, but it's just to make sure that you understand. And you're welcome to cut and paste this for other notebooks as well. If you feel like there's a notebook that you just want to read without the distraction of the code, cut and paste this in, and then you can sort of hide it and show it. Okay. So the aim of this Jupyter notebook is really just to let's go and visit the discrete problem, and let's look at the integral problem, how we would go about solving it in Python. Okay, so we know the problem. We're going to set up now for 6 values. So we're going to linearly spaced x values, 6 of them. Evaluate this expression, set up the system of the matrix system, solve for ABC using this optimal automatic tuning approach. And what I'm guaranteeing you is that the Z that we'll get from this solution is going to be absolutely optimal. Okay, I'm going to solve the system slightly differently. I'm going to solve the system in a way where I'm going to solve for A, B, and C. I'm not going to say C must be equal to, like, enforce the boundary conditions exact. I'm not going to say, for instance, oh, I know it X equals to this and whatever, that the C should be that value, and then I'm left with some smaller values. Exact value of C equals to 0 at that place where we have the, when I evaluate the displacement field at x equals to 0. I think that's how I derived it, if I recall correctly now, from 2 days or 2 blocks ago, or 2 lectures ago. But what I want to do is I'm going to solve this full 3 system. So I'm going to end up with a 3x3 system and solve a 3x3 system. Okay. Again, note this is different to what we will do in FEM. In FEM, we'll always make sure that where we have a prescribed displacement, so essentially if I remember this vertical displacement would be exactly 0 at x equals to 0. And that version, just to make sure that it's true. Yeah, you can see it's at x0, this whole thing goes 0. And then essentially what we see is that if I wanted to do it from a sort of the finite element point of view, I would say put in x equals to 0, and then C would be resolved to 0 to be exactly 0. And I would only be left with a 2x2 AB system to solve. But in this Python example, I'm going to solve the full 3x3 system, A, B, and C resolved, so I don't expect C to be exactly 0. So there's already something that's going to be slightly different. So it's important. So I want to demonstrate to you that the way we solve things dictates the kinds of solutions that we get, and we just need to get sensitized towards that and get comfortable thinking like that. So we're going to solve, in the end is A transpose A Z equals A transpose B, overdetermined system, and this is going to be optimal. Okay, I'm going to demonstrate to you that it's optimal as well. So first off, I get the 6 points where I want to evaluate stuff. I call it psi. I set up the problem. This is just the problem that I'm setting up here. Here's my expression for V. Here's my VI. So this is just V evaluated at psi, the xi's. This is my function that I want to try and fit. Variable 0, variable 1, variable 2, multiplied by x squared. This is multiplied by x. So variable's first index. The first index 0, but the first entry is for the quadratic term. That's our A term. This next entry is the B term, and the last entry is the C term. So now we can interpret as well what they are related to the A, B's, and C's. First off, I'm going to guess a solution, and I want you to play with these guesses. Come up with your own guess. But what I want to show you is, doesn't matter how long you guess, the solution we're going to get from this will be optimal. You can't beat this. This is the best we can do. Okay? And that's something that you can play with for yourself, convince yourself with. I'm, as a matter of fact, going to show you that even the solution we get with the integral approach, when I look at the error at those 6 points that I'm evaluating here, okay, at the 6 points that I'm evaluating here, this solution will be optimal. Okay, but bear in mind, you can't beat this solution if you want to look at the error only at 6 points. So first off, then I essentially create just a finer grid of points over 21 points, and I plot sort of the solution over those 21 points. This is just to visualize the fields better. This is now specifically the field of my guess, otherwise it's very jiggly. And that's that part, and then essentially I just compute the difference and I sum the difference squared, and this is sort of my guess solution. So this is just post-processing solutions. Then I set up my A matrix for my optimal solution. So now I'm engaging with the optimal solution of this discrete problem for the discrete system. We have multiple points where I evaluate what's going on. So I set up the matrix as first row is psi squared, next row is just the linear term psi, the last one is just the constant 1 for making sure, so that's what the C will multiply with, that's the constant, but these are all now rows, so I take the transpose to make it columns, so this is now a matrix. Then I compute A transpose A, then I get to compute A transpose B, yeah, and B in this case is just VI, that's where I evaluated for those 6 points. I evaluated what is the function value it's supposed to be from the solution here, that's what that is. That is A transpose B, and then I get my optimal solution by solving this little 3x3 linear system. Beautiful. And then I say, let's plot this now also over a finer grid of points so we can visualize it better. Okay. And if you do that, so that's that up to that point. Okay, I'm happy with this. Is just all post-processing. Then what I do in the end is I say, let's just compute the for those 6 points. Let's compute what is the difference between my approximation and my actual answer, what it's supposed to be. And remember, the approximation, the actual thing is a 4th order polynomial. My approximation only quadratic, so I can't satisfy it exactly. It will be some mistake there, but let's see how close I get. So what I want to then plot is that for those 6 points, what is the error? Okay, so that's essentially what I'm doing here. I'm plotting here for the optimal solution on the 6 points. This is the error that I'm plotting here. And then what I do is, later on, I'll plot also the error on the 1001 points, if I make the points more. But for now, let's focus on the 6 errors, 6 points. Okay. So if I do that, this is my guess solution. This is what it's supposed to be. The error is quite large. If I look at my optimal solution, look at that blue line fitting beautifully through those red dots. That's, as you can't beat this if you want to minimize the error at only 6 points. And this is what I mean, minimizing the error, I mean the residual squared sum. For at these discrete locations, we can't beat this. These are the optimal parameters. You can do what you want. You can play as much as you want. You won't be able to beat this. This error is the lowest we can get it. 2.5 e minus 7. Okay, that is important to understand. That's the lowest we can go. Let's go and look at the integral approach. The integral approach is just derived here by hand, just in the notebook for you, for your benefit. But again, this is the system we're going to solve. So when we look at the system carefully and critically, we see that the system is symmetric. So whether I have x squared x or x squared, same thing, it's x to the power 3. So this is symmetric, this is symmetric. So we have only 6 unique components. The diagonal and the upper diagonal part, those are the unique components. They've got the right hand side. So I need to compute in total 3, 5, 6, 9 integrals in total. Okay. You might expect, if you don't exploit symmetry, you might end up computing 12. But these bottom 3 are unnecessary. So please just take note. Okay, so these are the 6 unique terms of the matrix that I'm just integrating symbolically now, because I've created the x, a, b, and c symbols. Here I just integrate these expressions, code them in, and integrate them. Here I set up, this is a part of the problem setup. This is the right hand side. This is these expressions that I'm integrating there. This allows me to set up the system, the A system, and the right hand side, the V system. Now I can solve this little 3x3 system. Again, I'm solving the A, B's, and C's. And I just wanted to mention, so that, yeah, that's fine. We'll talk about it now. The A, B's, and C's. Where are we now? Okay, so we just solve that, and then I get the optimal solution, the optimal APC I get out of that solution list. So that's that. And then we can sort of start plotting the solution that we have. And then again, we can go and compute on those 6 points, what is the error. So I'm going to comment these things out first. I don't want to confuse the issue here now. Okay, so let's just run this quickly and let me show you. So first off, when I look at this, I say this is the optimal solution I get here. Here you can clearly see again, the displacement is not 0 at x equal to 0 because we didn't force it. We solved the 3x3 system. And the same is true here as well. When I look at the vertical displacement here, because I solved the full 3x3 system, I essentially see that there is essentially 0 there. Can you see that? That is essentially what I have there. that is not 0 there. So the C is not exactly 0, it's got some finite value, so that's not satisfied. This will be very different from a finite element solution. If I were to solve this using a finite element solution, I know where the pre-coupled expressions will be exactly satisfied. So please note, how we solve the system will influence what the values would be. Okay? I could have also solved the system, a 2x2 system, and forced the C to be 0. And then the answer would still be different. But this, for freedom of where I solve for A, B, and C, and the same go, to try and fit the data as good as you can, this is the optimal solution for the discrete problem. And the integral problem, we got this solution here. What I want you to note now is that the error here on the 6 points, if I compute the error for this integral solution on these 6 points, that error is 3.66E7. The error when I optimized, when I had the optimality criterion for those 6 points, yeah, using the discrete approach, is 2.5 E minus 7. This is lower. So you can't beat this. We can't beat this error here. This is the best solution if I just want to satisfy minimize the error at 6 locations. Even the integral approach is worse off. Why is the integral approach worse off? Well, it's simple. Because here we've minimized infinite number of points. We want the error across infinite number of points to be not only at 6 points. This is why the optimal solution for the integral approach is worse, because we actually considered way more points in the integral approach and minimize the error for those way more points. The way we can simulate that is to say, let's make the points more. And we can go back, and as a reminder, we also uncommented here at the top. So that's, I'm just uncommenting stuff that I commented out before. So what I want to do now is to say, let's check now the error at many more points. Okay? I just want to see what the time is, if I should maybe stop the video. So it's 11 minutes. We can now check the error at many more points and see what's going on. Okay? So what I'm going to do, in fact, is actually want to compute the error now for 1001 points. Let me see again, where did I do that? So this is the 6 points. Okay. So X error is a variable that I define at the top. I just want to show you where I define it here at the top. So here, let's go back to the discrete problem first, because this code is a little bit patchy. But anyway, so the bottom line is the X error I defined here as the 1001 discrete locations. I compute the Y approximation error for those 1001 locations. I compute the difference and I compute the sum squared. This is what I'm computing now. Okay, so what is important to understand here is I'm now computing the error not at 6 points but at 1001 points. And when I do that and I run this code, then I see that at the 1001 points the error is 3.53 E minus 5. Okay, 3.53 E minus 5. What I want to show you is that the error for the infinite number of points that we did with the integral approach, yeah, if I would evaluate at 1001, the error there would be lower than this error here. Because here, this solution here is optimal for error minimized at 6 points. So where was that now? This solution here, what happened now? Anyway, this solution here is optimal for the solution minimized, for the error minimized only at 6 points. So if I evaluate at many points, 1001 is just an example of many points, the error here is much larger than the error here. And let's see what it is for the integral approach. And my expectation is maybe that it will be lower for the integral, because the 1001 points is closer to the infinite points than what the 6 points is to the infinite points type of argument. But if 1001 is not sufficient, then it might still be that the other one might be bigger. But I think we should be in the ballpark that this one should be smaller. Let's see. So let's run this one as well and see for this one. So if I go now and I say, let's compute the integral optimal solution over 1001 points, I see my error is here 2.17 E minus 5. So this is 1, 2, 3, 4, 5, E minus 5, 2.17. It was, for the discrete approach, it was actually 3.5 E minus 5. So this is indeed smaller. The integral approach, if I look at many, many points, has a smaller error. Okay? That is beautiful to see. Okay. This is what we have. This error here is smaller than what we had. Okay, so that is important then on the discrete problem. But let's look at what is the error actually of the residual that we actually minimize. So remember we took the residual, we squared it, and we integrated it. If I go and I say, let's take the residual of my optimal solution, yeah, I compute the square of that residual, that's r squared, and I integrate. Then I plot that error for you. And let's look at that error. If I look now at the infinite number of points. So this is not now only at 1001 points. This error here is now at an infinite number of points. What the hell is going on here? I'm looking at more points and the error is lower. Why is this error larger than this one? Because here I only looked at 1000 points. Yeah. Here I looked at 6 points. It was low. The more points I look at, it seems like the number is growing. It's because of the way I compute the error. So the fact of the matter is, this error that I'm computing here, yeah, is different to just summing errors, because I'm actually integrating properly here, okay, over an infinite number of points. So there's a couple of differences between what we've done before and what we do here. So if I want to make sure that I compare errors that are similar to each other, I have to make sure that the errors have the same meaning, okay, and that they carry the same kind of approach of computation. So what I mean with this is, if I were to go and say, instead of just estimating this error as the sum of the differences, okay, this over 1001 points, if here I'm just computing the difference again as at the 1001 points, and I'm squaring and summing them. That's what I did before. That's not what the integral implies. The integral implies essentially, first off, that we also have to divide by the number of points so that we at least get the average error out, yeah? So that is essentially the one aspect that we need to do. And the other aspect is we integrate it from 0 to 1.5 in the integral approach, so we need to multiply by 1.5 here. This is going to be closer representation to the integral error than just summing the difference. The summing the difference and integrating an error is not quite the same, okay? Because the more points I'm summing in this difference, the higher the error will be, per se, yeah? So what I need to first do is to say, what is the average error over all the points? And for that, I need to divide by the number of points. And then I have to say, this integral went from 0 to 1.5. So if this integral is from 0 to 1500, the value would just be bigger because it's a larger domain over which I integrated. This does play a role, the domain of it, and this is then accounting for that domain. If I do that, and I look at this error that I'm computing here, then I see all of a sudden it's something like 3.25 e minus 8. Now this discrete sum of errors is relatable to at least the r squared integral error. And now they're talking the same language. And what we see here is this error is still slightly lower than this one. But here it's because I only looked at 1001 points. At the top, I looked at an infinite number of points. So hopefully this gave you a good example of how we can go about computing for the discrete and for the integral approach, but also more importantly, critically reflect on what we're computing, what errors we're computing, how we're computing the errors, and that we make sure that when we want to compare things with each other, at least we do it in a relatable way. That we don't just compute an error the one way, like summing of the difference squared, and the other error we compute as an integral kind of approach, and then we try to make sure that they're the same. We have to make sure that we compute errors similarly if you want to be able to compare them. Okay, thank you for that, and I'll see you in the next video.